Okay, so I know this, you've seen this already, and you're saying we should be here, but I want to step back just for a moment to put a little calculation over here. And so if you have your notes, if you've been writing those, which I highly recommend, um, let's look at the cost per mile to drive an electric vehicle. This is really an important point, and it's rare to find someone who even knows this because it's not something that we would think about on an everyday basis. But people are almost always surprised when I show them. Okay, so I just looked up a Tesla Model 3. It's now, I think, the best-selling electric car in the United States. And it gets right at 3 miles per kilowatt hour. And let me just put a W there because that's actually what I'm supposed to have there. 3 miles per kilowatt hour. Okay. What does a kilowatt hour of electricity cost? Because then we could figure out the cost per mile. So it turns out that at my home, I'm paying 8.5 cents. Some people pay, I think in Monmouth, people pay a little less. If you're, and we're both in what's called public utility districts where they're not trying to make a profit on electricity. And they also have good buys on the hydro, which is most of their portfolio of sourcing. Some people are paying as much as 10 or 11 cents in Oregon. Okay, it depends on where you are. But let's use my number is a little under 9 cents. Let's use 9 because it's really easy math, right? You already know where I'm going with that. So if I have 9 cents to go 3 miles, that's 3 cents per mile. $0.03 per mile. Now, what about a kind of similar sized and performing conventional gasoline-powered automobile? Let's say it gets 30 miles per gallon. 30 mpg. And what's gasoline now? Let's say it's 240. Okay, every time we do this calculation is different, so I always have to do the math over again. But let's say it's $2.40 per gallon. So if you go 30 miles on 240 cents, that's, you got that figured out, right? Yeah, it's 8 cents a mile, isn't it? Wow. That means if you compare those two, it's between double and triple the amount of energy cost per mile as gasoline. And the cost of electricity might actually keep going down because as wind and solar become more abundant and cheaper, we might see that change. Now, some of you might remember, wait a sec, you showed me where wind and solar are down to 3 or 4 cents in some places. Yes, I did show you that. But remember, it takes some cost to distribute and retail that to you. So that's how you can go from 3 to 4 to 5, 6 cents up to 8 or 9 or 10 or 11 cents, okay? But the retail price is what I used here for both. And it's way more money to drive a gasoline-powered vehicle. Okay, so thank me for that one, huh? Isn't that amazing? I love to show that. I've been showing that for years, and it's always fun, and students are almost always surprised, although I've noticed lately some students are onto this. That's really good to see. Okay, awareness is going up. Okay, so now going back to going onward rather to our next slide. So the distributed electrical vehicles to the grid is a strategy that we might do someday. And imagine if a third of us are driving electric cars and we can store, you know, a lot of these are storing like 100 kilowatt hours or more of electricity. That's a lot. That's more than a house uses in most people's houses. My household, we use about 17 kilowatt hours per day on average year round. I figured out once something, no, it's actually a little less than that, maybe 16 if I remember right. So that would be like a Model 3 now, nicely charged, would hold enough electricity to, was that 20 days? That's amazing to think about that. No, excuse me, 6 days, 6 days. Anyways, let's not get lost in that. Another thing that can be done is demand side management, and that's where you have your house set up, managed to just use the electricity for some things when it's needed, like if maybe you're going to dry your clothes or run the dishwasher or that sort of thing. Some of those things can be staggered, and you can save some money there if you wait till the electricity is cheaper. And in some states, they have a system like that. Texas does, interestingly. And so there's if you're curious about that, you can just Google demand side management. I'm not going to spend more time on that now, but there are significant changes. Maybe 10 to 20% of a load can be shifted in some kinds of households. Sometimes preheating or pre-cooling works a little bit as well, depending on pricing. They have that in Arizona as well, by the way, at least in Phoenix where I lived. Future. Okay, so these are big things here. Because one of the things we looked at is that our wind energy kind of stalled in Oregon and Washington, hasn't grown much. A lot of that is just because cheap natural gas came in and kind of replaced the coal. It's a flexible fuel, and so it's not entirely clear to me what will happen with the wind energy industry here in the Pacific Northwest. One of the things that developers that we're just now catching up with is how cheap solar is. And I ran some numbers. Maybe I'll share them with you at some point before we're done, not on this presentation, but maybe with this unit eventually. But Oregon, there are some kind of like 100 megawatts scale wind farms in Oregon. We could do a lot more, and it would be something we could price pretty close to grid pricing in the middle of the day. So some possibilities there, kind of interesting. So the other things that are kind of the sleepers, one is the wave industry, that we don't really have one yet. It's still in the experimental stage. I want to show you a little bit about that here in a moment. Oops. And the other is the offshore wind energy, and we talked about that already. I want to show you a couple things on that. Let's see, I've got one thing I'll quickly show you is a little bit about the pumped hydro. There was an article, and I've got that link for you, so you'll find that on the Moodle site. Don't worry about looking for it now. But what I'm looking for is, and this is kind of fun. Texas grid has a nice mix of, in some areas, of coastal wind and solar, and then, inland wind and solar. So this would be their solar curve, and then, which is the yellow. That's nice and easy to figure out, right? Wind is the dotted. See how that is a nocturnal thing, and then not much during the middle of the day, and then it comes back up at night again. And so the two of those mix nicely and create a net load, which is basically more or less the sum of the two. And so you end up with a pattern that works kind of well. But as solar becomes more important, they're going to need to figure out a way to store. So something to think about. I need to figure out where I'm at with time. Okay, we're good with time. So I wanted to show you this article about offshore wind. It grew 19% globally in 2019. It's a big thing. I just wanted to show you this, a little bit about this. This is just kind of the project pipeline. The pipeline doesn't mean literally pipe, just means the projects that are in the works, okay? And so they are going into deeper and deeper waters, and the more a greater distance offshore. The wind energy profile in Oregon is kind of interesting. It is very much more powerful offshore, which we looked at, okay? And so this may be our kind of next thing, and this is kind of how those look. With this new technology, I wanted to show you this, really interesting. They can go really deep with this particular approach, and some of it was developed actually using floating offshore oil drilling and pumping platforms in the North Sea, in the deeper parts of the North Sea. And so there's some belief that this could be adapted to the even deeper offshore waters off the Oregon coast, going out maybe like 7 miles or more, where the wind is really, really strong and where people really wouldn't see the machines out there from the shore, which is something that a lot of people don't want to have to do in a place where tourism is really how you have an economy, employ a few people in those kind of areas. So that's something to think about. Let's look a little bit now. We've got just about 4 minutes. I just want to take a quick peek at this with you. There's some really exciting stuff, but it's still futuristic about, I'm going to pause this just for a moment. Okay, so much of this slideshow is composed of slides utilized from the Wallace Energy Systems and Renewables website at Oregon State University. Unfortunately, the program has been mostly defunded. The federal funding for renewable energy research has taken a big hit in recent years. I wish I could say otherwise. It's just the realities. But this may be a big part of our future. It's just been delayed some. Let's hope for the best. But let me show what that's all about. Who knows? It might pop up. So the basic idea is that the wind blows over the waves, over the water, and its kinetic energy, some of it's transferred to the water, so you make waves, which have a circular motion kind of up and down like this. And so if you put something there to capture that, you can, I'll show you that and I'll come back. Something like this where it moves up and down. And then there's a generator inside. As you can see here, that coil on the magnetic shaft goes up and down, and that will generate electricity, okay? It's kind of a pretty diagram, isn't it? Okay, we don't have any cities on our coast like that, but fortunately, I kind of like the small towns. But anyway, so going back then, but the things to know about wave energy, one is very high energy density. If you just take a line along and per wave, a stretch of 1 meter gives about 30 kilowatt hours per meter per day. And that's quite a bit. That's like enough for, let's see. Well, that's more than enough for the average household, just to give you an idea. 1 meter of width on the Oregon coast, to give you a sense of that, okay? And with solar, although the comparisons aren't really fair because solar is an area, that's actually a linear measurement, the way that's done, and wind are much lower. Anyway, high energy density because that's water. So the higher energy availability of wave energy is really, really high. Some of the very best wind farms, even in offshore areas, might come in at almost 70% capacity. Very, very unusual to get that high, though. With wave energy, the availability is 80 to 90%. It's very predictable because, first of all, the winds are now fairly predictable, and the winds are what make the waves. And very often the winds are very far away from the coast, so they make the waves somewhere far away. We know they're coming. We have offshore buoys, ship reports, and so on, and we're able then, with a fairly high degree of certainty, know the size of the waves as they come in. The predictability is wonderful because then the system operators for the grid know what's coming and they can plan accordingly. The seasonal cycle, this is really important. The seasonal cycle is a good fit with the current Pacific Northwest supply and demand because the wave energy has a winter maximum, whereas our other major source, natural hydroelectric, has a winter minimum. So this is perfect. This is our winter problem when we buy fossil fuel generated electricity. The wave system could do it. And most of the U.S. population lives about 50 miles from the coast. That's a plus, too. And that's true here in Oregon, too. Most of us don't live all that far, really, maybe 50, 60 miles. Okay, and so some numbers here. You can pause this if you want to look at it. But basically, west of the Cascades, we consume more than we generate. East of the Cascades, we generate more than we can consume. Some of that was from the wind, some of that's from the solar, some hydro, okay? So there's this kind of imbalance and all that. That would be kind of nice, okay? And then the winter average of the wave is about 50 kilowatt hours per meter. The summer is 10, okay? And so we're talking about a lot of, that's like Grand Coulee Dam in terms of capacity, that sort of thing. It's huge, okay? So don't have an